Okay, let's start the morning session. So this is the last day of this great SAPS conference. So as I personally learned a lot from this conference, and thanks to all the speakers. So this is our first speaker in the morning session is Gabriel Wong. He's from Oxford Universities, and he's expert on the holography and also entanglement entropy, content information, and also topological string. So he will tell us about gravity, entanglement, and quantum chaos. Let's welcome.
Thank you. Well, first of all, thank you very much for the opportunity to give this talk. I've really enjoyed this conference and this beautiful surrounding here at BIMSA. So today I want to talk about sort of the general question of how gravity emerges from quantum mechanics. Now, naively, quantum mechanics and gravity seem very different. Quantum mechanics is really about linear algebra, just the theory of matrices and linear equations. And the problem is just to diagonalize the maybe gigantic matrix, find its eigenvalues and eigenvectors, and get a discrete spectrum. On the other hand, gravity is about geometry. It's a theory that involves nonlinear PDEs, smooth manifolds, whose solutions have interesting causal behavior, such as black holes with horizons, or in Euclidean nature, non-trivial higher topologies like wormholes. So in this talk, I want to explain how quantum chaos and the phenomenon of entanglement relates these two apparently different-looking theories. Now, I'm going to split my talk into two parts. So the first part will be about gravity and chaos, and then the next part will be about gravity and entanglement. I'll be a bit brief here in the first part since I've given this talk maybe quite frequently in recent times. So let me start by an introduction to chaos and random matrix theory. The best, I think, physical example we have of this is the study of heavy nuclei, which Wigner and Dyson undertook back in the maybe 50s and 60s. They were studying very complex nuclei, which has a very big Hamiltonian, a difficult matrix to diagonalize. And they said, let's forget this matrix and just treat each entry as a random variable. So we replace one matrix with an ensemble of matrices with some choice of potential. And it turns out that if we were interested in the universal features of the system, like the distribution of nearest neighbor eigenvalue spacings, then the random matrix does very well. So here's the histogram for some uranium isotope. And the smooth curve is the RMT result, and they look pretty close. I don't exactly remember what they studied. I mean, I think they probably, I'm not sure which applies to the uranium, but I'm sure that Wigner studied GOE and GUE as well. Yes. So, so here I'm going to give a definition of a quantum chaotic system as a system that's well approximated by RMT. In particular, what it means is that averaging over energy window, which is what happens when you try to replace a histogram with a smooth curve, is equivalent to averaging over an ensemble. That's sort of the real power of quantum chaos and why RMT does well. Now, as we said, so RMT averages over discrete spectra of individual chaotic systems. So this discrete finely spaced spectrum gets replaced by a smooth density rho naught. The reason there is universality in this story is that there is a universal eigenvalue repulsion that comes from the measure of the random matrix integral. So here I wrote the measure in terms of the matrix elements. I might have, these are Hermitian matrices. I should probably have put GUE here, but I wanted GOE for the future references in this talk. And when you go to the eigenvalue variables, there is a Jacobian. The Jacobian is called the Vandermonde, and it gives you an eigenvalue repulsion potential. If you exponentiate this, you get log of EI minus EJ. And this Vandermonde is just determined by the symmetry class of this ensemble. Now, again, there was a typo here, but here I've chosen the exponent 1, which is for the orthogonal ensemble. So random matrix theory is well suited to study universal features of quantum chaotic systems. Now I want to discuss chaos in gravity. In ADS-CFT, we know that black holes are due to large complex systems with an enormous number of microstates. The kind of coarse grain density of states is given by exponential of the area over 4g Newton. So, and we also know there are some signatures of both classical and quantum chaos. So it's fair to ask, can universal features of quantum gravity, in particular black hole physics, can they be described by random matrix theory? Now, famously, in the case of Euclidean ADS to gravity, Sachenko and Stanford showed the answer is yes, there is indeed a random matrix theory that describes 2D gravity, or 2D sine dilaton, 2D dilaton gravity. Now, our work with Daniel Jeffers and Lisa Rosenberg was to lift this duality into 3D and to relate ADS3 gravity to an ensemble of 2D conformal field theories. This was a follow-up of some previous work by Berlin de Boer, Jeffers, Nag, and Sonner. Now, let me start by reviewing the 2D story as a warm-up. In this story, the matrix model observables give boundary conditions for 2D gravity. So here's an observable is the partition function of the Hamiltonians in the matrix model. And when we take its average, we are inserting a circle as the boundary condition for 2D gravity. And the 2D gravity path integral instructs us to sum over all topologies that can end on this circle. Now, in this story, Euclidean wormholes between disconnected boundaries play a key role. The reason is they describe the connected higher moments of the ensemble. So if I have two insertions of z beta 1, z beta 2, we have a boundary condition given by two circles. There's this disconnected topology, which gives us a disconnected contribution. But there's a physically connected topology, the double trumpet, which gives us the statistically connected two-point function. Now, in this story, there's an interesting sort of recursion relation that allows us to compute observables. So the random matrix theory has a topological expansion in terms of genus parameter, which is the inverse level spacing of the eigenvalues. And this expansion is actually computed using something called matrix model recursion. There's an algorithm by which we take two inputs, the disk level partition function and the annulus level two-point spectral two-point partition function. And from these two inputs, we can get all the higher genus and higher moments from matrix model recursion. The gravity dual of this is topological recursion, in which now here we're talking about the physical disk. Here the disk, the annulus refers to this genus parameter here. In the gravity case, these are actual manifolds, and knowing the gravity path integral on these two manifolds allow us to produce all the other higher topologies using Mirzakhani's topological recursion. I want to give a sort of conceptual perspective on this topological recursion. So just like in statistical physics, the ensemble interpretation of quantum gravity is giving us the best description of a system, but subject to a constraint. Now, best here means maximum ignorance. In some sense, it should maximize some kind of Shannon entropy. And the machinery of topological recursion is producing for us a maximum ignorance ensemble, but subject to the input given by the disk and the annulus. This determines the spectral density and the symmetry class of the ensemble. So now let's go to the 3D case. We now propose that there's an ensemble of conformal field theories. I'll explain why this is an approximately conformal field theory later. But we know that CFT is much more complex than a matrix. The reason is it has a local operator algebra, and it satisfies the constraints of space-time locality that's captured by the bootstrap equations. And the punchline of the story will be that the sum of the three manifolds in 3D gravity, including these wormhole topologies, is implementing these constraints. So these are, if you will, some extra constraints that we input into this maximum ignorance ensemble. So what is the ensemble data? Now in the CFT, our partition function, instead of being on a circle, is now on a torus. So we have a Hamiltonian, but also a conserved charge, the momentum, that performs spatial translations. And we're going to look for random statistics inside each sector of fixed spin, fixing the eigenvalue of P. This is important to avoid some spurious degeneracies that just come from symmetry. And so what we have as ensemble data is now an infinite number of Hamiltonians, one for each spin. If you want, this is what you get by diagonalizing H and P simultaneously. This is the Hamiltonian inside one block for each spin S. And we have also a three-legged tensor, the OP coefficient. This is our ensemble data. And we need to impose the constraints of 1-point modular invariance on the torus and 4-point crossing on the sphere. Our ensemble partition function, if we were interested in exact CFTs, would involve a product over all spins, integral over these matrices and tensors, and an a priori potential whose job is to produce the spectral density that's equal to the Carty density of a CFT. This is an input to our story. The Carty density gives us the black hole density of states, as we know, so we want that as part of the input of the ensemble. Now, this delta function of the constraints poses some challenges because we're interested in irrational CFTs with a large central charge, and for which we don't know any solutions of these constraints, except maybe Liouville's theory, but that's for that's just the only solution that we know. So what we want to do is smear the delta function in order that we have really an ensemble to average over. We want to have the possibility of e to the s number of elements of ensemble to average over. If we had to localize to exact CFTs, first we don't know that space, and we also think that space is sort of sparsely populated. It would not be something we can easily average over. So we smooth out the delta function with the constraint squared potential. This potential is literally defined by taking our bootstrap equations as constraint equals 0. We square the constraint, and then we put a coefficient here so that h bar is going to be small. That means the potential will heavily favor the CFT data that actually satisfies the constraint. But they don't satisfy them exactly, and that's why we call this ensemble of approximate CFTs. And the hope is that when you take the h bar going to 0 limit, this ensemble will teach us something about the space of exact CFTs. So let me give you an example of a potential that imposes the constraints. So we're interested in the 4-point sphere crossing. First, notice that the Virasoro conformal blocks form a vector space with a particular inner product that was formulated by Verlinde. So here I've written the 4-point crossing equation with conformal blocks written as some kets in this Hilbert space. And we're going to use this inner product to square this equation. This inner product is actually the same as the inner product of Virasoro TQFT as formulated by these authors recently. When we square the constraint equation, we get a quartic potential in the Cij case. Now, I'm not going to go into too much detail, but it turns out that if we study the Feynman diagram expansion in H bar, which is the coupling of our theory, we get the following Feynman rules. Because we have Cij 3 indices, we get triple line Feynman rules. So here's a propagator. I'm sorry there's a typo here that I neglected to fix. This is I, L, J, M, K, P, and the propagator just makes sure that the indices align. There are these two vertices in this matrix or tensor integral, and they both are equal to some data of the representation category of the Virasoro algebra. For example, this is a modular S matrix of the Virasoro algebra, and this is a 6J symbol of the Virasoro algebra. It turns out that these Feynman diagrams reproduce exactly the 3D gravity amplitudes on hyperbolic manifolds built out of these three type of wormholes. So each Feynman graph is mapped to a wormhole. The wormholes can be thought of as being obtained from S3 with 4 balls removed and a pattern of Wilson lines inserted. So we call this guy a pillow graph inserted inside this 4-boundary wormhole, and this we call a 6J inserted in this 4-boundary wormhole. This is S3 with 2 balls removed. It's equivalent to just S2 times an interval, and there are 3 lines going through it. Now, when we compute observables of the tensor model, we're inserting CIJKs. Those are the things that we want to average. And each insertion now is inserting a 3-punctured sphere on the boundary. The Feynman rules tell us to attach these wormholes to these boundaries. So for example, the average of Cijk would involve, at the leading order, an insertion of this S2 times interval wormhole. And this other 4-point OP coefficient gives us the 4-boundary wormhole plus corrections. Yeah. Yeah, you can think of, so yes, we can think about it that way in terms of the punctures or the primaries. And then we can think about in the sort of Chern-Simons formulation of gravity, these would be Wilson lines. But in just pure gravity, we can think of them as, well, there are different types. In 3D gravity, everything's topological. So in the bulk, there are objects that are like kind of defects, they're conical defects, but there are also defects of the hyperbolic type. And these heavy lines are the defects of the hyperbolic type. They're like black holes in some sense. They're microcanonical black holes in some sense. But I think maybe, yeah, they indeed are in one-to-one correspondence with the primaries of your CFT, which extends into a line in the bulk. Now, I want to make, this is going to be my final comment about the ensemble. The matrix model produces much more interesting off-shell manifolds. What do I mean by off-shell? Well, first of all, the matrix model inserts toroidal boundaries. The reason is that the partition function of CFT lives on a torus. Here, I've chosen to Laplace transform the partition function into the density of states. So the 2-point spectral density would insert 2 toroidal boundaries. And the simplest wormhole topology is just the T2 times interval. This is off-shell in the sense that there's no solutions to Einstein's equations. It's not a hyperbolic manifold. Now, this torus wormhole produces for us exactly the inverse Vandermonde of ensemble. Why? It's because the 2-point spectral density here to leading order is giving us the inverse Vandermonde because the Vandermonde appears as the quadratic kernel for the density of states. If I wrote our matrix model in terms of density of states, you see the quadratic term in rho is given by the Vandermonde. So the 2-point function should be the inverse of the quadratic kernel. So it gives us the inverse Vandermonde. So this topology is telling us about the random matrix statistics of gravity. Now, one of the features of this non-hyperbolic manifold is that it has a non-trivial mapping class group. This is a group of large diffeomorphisms that are not connected to the identity, and in particular has a z times z mapping class group. You can think of it as what you'll get if you cut this torus wormhole in the middle here and try to glue it back together to construct the T2 times interval wormhole. When you do that, you have a choice of twisting along the 2 cycles of the torus. But you can only twist up to like 2 pi or something. So that's why you get z times z, because the Dane twist is quotiented out by gravity. It's a large diffeomorphism. Now, this would not be quotiented in TQFT. So Virasoro TQFT does not give the same answer as gravity. So Kohler and Jensen and also Cynthia Yan very carefully computed the gravity answer on this wormhole, accounting for the quotient. And it turns out that it reproduces exactly the inverse Vandermonde for the GOE ensemble. It gets even this sort of, there's a factor of 1 here coming from the exponent, and gravity actually gets it right. Now, the GOE is the right symmetry class for basically ensemble of QFTs because there's generically a CRT symmetry, which is a bosonic symmetry that squares to 1, and that lands us on the GOE ensemble. So I think this is a very interesting fact because this is a feature of gravity, right? The diffeomorphism invariance comes from the equivalence principle, and it seems like it lands us exactly on a particular symmetry class of the dual ensemble. So I think it's a very nice illustration of how sort of pure gravity connects to quantum chaotic systems. Before you sum over SL2Z, yeah. Okay, so now I want to transition to the next part of my talk. So as we sort of demonstrated with the torus wormhole, the gravity path integral allows us to access universal features of quantum gravity. But what if we want to learn about microscopic features? In particular, the black hole density was really an input into our story. We put it in by hand. How do we see then the microscopic origins of gravitational entropy, which depends on this density of states? So yeah, so the thing that's not the input, for example, is the higher moments, right? So I will call these the output. When I do the Feynman diagram expansion of my tensor, then what it does is it wants me to connect boundaries with wormholes. And because this expansion in some sense is taking h bar small and expanding small h bar, it's trying to get us closer and closer to the ensemble of exact CFTs. Because if you remember, h bar was a parameter that parameterizes the violation of the bootstrap. So the higher moments is not an input. The ensemble produces that as an output. Now, it's true for the matrix model. I didn't explain the sort of higher topology story. I didn't explain the potential for the matrix model. I just wanted to get to some other part of the talk. But in that case, you'll have a potential that implements SL2Z modular invariance. And that would be important. I can tell you what happens. So there, you can imagine doing the, whoops, what happened? Let me just say a word about what happens in that story. You can imagine that the simplest class of 3 manifolds that appear, if you study these toroidal boundaries, right, is to just attach a circle to the 2D matrix model expansion. But that's not enough. That would be what you get from what I call the a priori potential, before we impose SO2Z modular invariance. In this story, we, in addition, added a potential that now squares the SO2Z modular invariant equation. Interestingly, we have to use the gravity inner product to do the square, and not the TQFT inner product. So I should say the choice of inner product, choice of how to square the potential, the constraints is also an input. When we do that, what we get now is again a sum over 3 manifolds, but now the circle is non-trivially fibered over the 2D manifolds, and it will include a complete sum over like Seifert manifolds. And these were understood previously to be important to fix some pathologies like negative density of states that appears if you summed over SL2Z images of BTC black holes and so forth. So there's an interesting story there too. Unfortunately, I didn't have time to go through that. Any other questions before I move on? Okay, so I'm going to go to maybe an older story in ADS-CFT about entanglement and bulk geometry. So the main lesson we've learned over the many years of studying ADS-CFT is that in this story, the bulk geometry sort of emerges from the entanglement structure of the boundary. The most striking example of that is the equivalence between gravitational entropy given by the area of extremal surfaces and the entanglement entropy of the boundary theory. So the most general formulation of that is just to take any extremal surface in the bulk at a fixed time slice that is anchored on the boundary on codimension 2 surface. In this picture, it's just 2 points. Now, the codimension 2 surface here is the boundary into 2 regions, 2 spatial regions, and the area of this extremal surface is computing the entanglement entropy between these 2 regions here. Now, this is the most general case. A specific case of that is a 2-sided black hole, where the horizon area here is, this is the minimal surface. It computes the entanglement entropy between the entire Cauchy slice of one boundary with the Cauchy slice of another boundary. Now, we can be more specific about this. So what is the actual state that we get, the entangled state of this 2-sided geometry? The state here is prepared by this Euclidean disk. And this Euclidean disk prepares a thermophile double state, which is the entangled state of the left and the right boundary series. That's a very nice story, but in this talk, I want to ask how to understand gravity directly from the bulk. Can we see that the features of geometry emerges from bulk quantum gravity? In particular, is there a bulk notion of entanglement entropy that might equal gravitational entropy? Why is this important? Well, first, what the bulk is where observers live. We live in the bulk. And in particular, in de Sitter, which is likely our universe, there's just no spatial boundary to anchor a holographic stream. So gravity never turns off. So we have to ask, does it even make sense to talk about entanglement entropy when there's really a fully gravitating space-time? In particular, what does it mean to factorize the Hilbert space of gravity? What is the notion of a subsystem in gravity? And to get a notion of entanglement entropy, we will need a trace, which has been a subject of intense study in the past few years. Now, this factorization question has a precise formulation in terms of a Euclidean path integral process. It requires something that I'm going to call a shrinkable boundary condition. This was coined by Jeffress and Koschmeyer. And I want to argue that this defines a type of local holography. My main goal is to explain how this works in topological string theory, and quantum groups will play an essential role. So the topological string probably just creeped up on you in this talk. It was not in my abstract, but it is a toy model. In principle, it doesn't have gravity, right? It doesn't have a graviton, but it does have one important thing. It has geometric transitions, which is the stringing mechanism behind holography, and that's the feature I will focus on. Right, so how do I factorize the Hilbert space of quantum gravity? Because so here, maybe I can say in this story, the CFT obviously factorizes because we'll have 2 disconnected CFTs, and I'm now not doing ensembles. I don't want to look at universal features. I want to look at something that's not universal. So the CFT, by definition, factorizes. So the bulk, if there's a duality between Hilbert space, the bulk also factorizes. But because the bulk is connected, it's not obvious how it factorizes. Even if I studied gauge theory on this bulk space-time, so Dan Harlow had a paper quite a few years ago explaining that if I consider a Wilson line that threads this wormhole here, it doesn't look like it factorizes at all. There has to be some object in the bulk that splits the space-time, and that's what I want to discuss. Well, in de Sitter, I could ask the same question. So what the point is that if gravity turned off, I could easily split. So if there was no gravity, I could just say I have QFT on a fixed background. Then the factorization is no more severe than factorization in QFT. And I'm happy with factorization problem QFT. I just put a regulator, and that's what I was going to explain. So let me explain this first slide, and maybe it'll answer your question. So first, I'm now going to give an overview of what I call shrinkable boundary, and something that was coined by Jake McNamara, something called EPR surgery. So let's take QFT for the moment. What is the factorization question? The Hilbert space on a Cauchy slice, which now is to be de Sitter. This is a Cauchy slice, which is just a closed surface. The Hilbert space is not a tensor product of a Hilbert space on V and V bar. Why? Because of energy constraints. The Hilbert space of the total Cauchy slice is made of finite energy excitations above a vacuum. And the tensor product here will contain infinite energy states. Why? Because if you think about, say, even a classical field configuration, they could have arbitrary kinks. They don't have to be continuous, and then that kink will produce infinite kinetic energy. But that, I think, is an easy problem to solve. We just put in a regulator. That's what we always do in QFT. If we put a regulator, then we can study an embedding I, depending on the regulator, epsilon, that embeds the physical Hilbert space of physical states into the tensor product. It will embed it into low energy subspace of the tensor product. But that's fine. We can still trace over one side, compute the entanglement entropy, except this entropy will diverge as we take the regulator to 0. So we put a stretched horizon here. Maybe I shouldn't call it a horizon. It's a stretched entangling surface. And now we have a well-defined factorization and entanglement entropy. Now, in a gauge theory, the Gauss-Dart constraint gives a more IR obstruction to the factorization. So why is this true? In gauge theory, there are non-local objects like Wilson lines. And the entanglement surface will necessarily cut these Wilson lines. But suppose we are doing pure gauge theory. Gauss also says there are no charges. So there are only Wilson loops. If I put in an entanglement surface, I'm caught with this problem that I'm going to cut some of these Wilson loops. So to factorize the Hilbert space, I really have to lift the Gauss law constraint that crosses the entanglement surface. That's fine. We understand this phenomenon. When we do this, the would-be pure gauge degrees of freedom on the boundary is promoted to physical degrees of freedom. These are edge modes, and they allow the Wilson lines to end. There's some charges here that make gauge invariant Wilson lines here. Okay. Now I want to, and of course, the reason I mentioned gauge theory is gravity is a gauge theory. So you might think in gravity there are also such kinds of edge modes. Now I want to give a more precise definition of the factorization map that will be useful for this talk. Well, first, the factorization map should be isometric. It should sort of preserve inner products. I'm going to define it using a path integral process. I imagine a Cauchy slice here. I evolve it in Euclidean time in a way that splits the Cauchy slice. But then I have to tell you what is the boundary condition along this little curve here. Whatever it is has to have the property that after splitting, I can fuse it back, and that produces the identity map. Because the entanglement surface is not a real surface, so it should be totally transparent. What does this mean if I were studying, say, a thermal field double state on a fixed background? In the unfactorized preparation by the path integral, I have some state on the full Cauchy slice. But when I attach this factorization map to this blue line here, it splits the Cauchy slice. And now it looks like it will produce some entangled states in the Lorentzian continuation. Now, this it looks maybe hard to understand what this corner is here. So I'm going to define shrinkability using by capping these off, by studying the Euclidean sphere or Euclidean disk partition function. So if this were the two-sided ADS black hole, then we'd be studying the disk. If this were de Sitter, we'd be studying the sphere, which is just the Wick rotation of the space-time. So we're going to use the Euclidean path integral to compute the partition function on a disk. And the statement of this shrinkability is to say that if we put in the shrinkable hole, in the limit as the size of the hole shrinks to 0, it should give us back the disk. That's what shrinkable means. But then what's the point of putting in the hole? The point is that on this side, it's manifest there's a non-trivial, a non-contractible cycle here, which we can take as the temperature cycle. And therefore, this defines a trace. Yes, the boundary condition was I labeled by E. Well, I think it's okay to think about it as the boundary condition is a boundary condition on this interval, and when we quantize on an interval with boundaries, we should put boundary conditions, right? Sure, exactly. That would be the difference. So in Maxwell, it is local. So that's the subject of this work here. So in Maxwell 3, for example, it is local. We think in Yang-Mills it probably is also local, and in QFT, there are ways to define local boundary conditions that would satisfy the shrinkability. For example, in 2D CFT, this is very cheap. In 2D CFT, almost any boundary state. If I imagine that the state on a circle here is a boundary state of a CFT, anything that has non-trivial overlap with the vacuum will shrink because when you make this hole very small, it's like in CFT, you can think of it as a long propagation, and that will project into the vacuum. But the vacuum state, by definition, in CFT is what fills in the hole. So, yeah, it's okay. There are subtleties, but I think we can work with these subtleties in QFT. Well, V is the interval. Sorry, I didn't write it. V is this interval. Oh, sorry, you mean the Hilbert space on V. Yes, but once I give you a boundary condition, I can quantize, I can define V that way. Yeah. I'm not trying to say that this is easy or it works generically, but we've been studying this in various systems where it works. And certainly in low dimensions, 2D Yang-Mills, 2D CFTs, 4D Maxwell 3, we know it works. But I want to say that this definition here also gives us a state counting interpretation of, I call this SGen, but you could call this a geometric entropy or replica entropy, where you take the partition function on a disk, you compute log z and take this pattern of derivatives. Beta here is the angular range of this temperature circle. Now, when I write down this formula, it's not automatic that this has a state counting or statistical interpretation, precisely because this thing actually doesn't shrink. The circle here is actually not contractible, so we don't know that there's a trace. And as Chengbin mentioned, there could be subtleties about this trace. If I would succeeded in giving you this local boundary condition, then I could produce this trace and sort of almost by construction, putting this hole here successfully produces a trace over some kind of density matrix on this interval I call the V. That gives a statistical interpretation to this kind of entropy. Now, in QFT, when I vary beta, I keep the geometry, everything else in the geometry fixed, so I produce a cone. And that produces a divergence in the entanglement entropy. When I put in the brick wall with the edge modes, I'm shrinking to the cone, so this story will also produce the divergence, but it interprets the divergence in different ways. So, well, first, the divergence is something we accept in QFT. It's just that we put in regulator and it diverges when the regulator goes away. But it's well known that in Maxwell theory, the cone here gives a contact term in the entanglement entropy. And this was computed by Wong and Donnelly as a very precise coefficient, is a log of the radius of the entanglement sphere. And we reproduce this using the shrinkable boundary condition. So the shrinkable boundary condition is very simple, is that the gauge field going along this direction, the component of the gauge field going around this circle has to be 0 at the boundary. And that produces edge degrees of freedom, whose entanglement entropy is exactly this minus 1/3 log R. Epsilon was the thing that I showed earlier, is this epsilon here, that is the regulator, so that allows this embedding to be well defined. So it separates the separation. It cannot be 0 in QFT, but the point of this review is to see how it changes in gravity. In gravity, we don't put in some regulator by hand. So what happens in gravity? Well, I think sometimes people maybe are confused or puzzled that what I call edge modes look like they break gauge invariance. But that's not a problem because it's important that the subregions are in. So when I define a subregion in gauge theory, I close it off with edge modes. It's a self-contained system. The point of view of the subregion, there's no violation of gauge invariance because I've lifted what was pure gauge degrees of freedom are no longer pure gauge. Gauge transformations that are non-zero at the entanglement surface are not allowed in the subregion. They're not gauge, right? It's just like Schrödinger story with soft modes and infinity. There are what people call large gauge transformations, which are gauge transformations supported at the boundary. They're not pure gauge in the subsystem. So in the substance, it's no problem, okay? But now I have two subregions, and now I define the thing that may be confusing is that in the original system, there are no edge modes, right? So what happens is that in this embedding, the entanglement is going to project onto a gauge invariant physical state in the physical state. So each HV and HV bar contain states that violate Gauss law, but this embedding only lands on the states that satisfy Gauss law. So there's no contradiction with gauge invariance. Or simply put, in the two regions, when I do a simultaneous gauge transformation on this side and on that side, the physical state is invariant. So there's no violation of gauge invariance when I study the actually entangled states. The violation of gauge invariance would seem to appear if I mixed up this picture with that picture. But I think I'm trying to be very careful saying that I define an independent self-contained system here, self-contained system here, and I define a fusion by entanglement that produces a state that is isomorphic to states here. At every step of the way, gauge invariance is completely preserved. Good. So I want to get to gravity. So how is gravity different? In gravity, we also, I should probably put a beta here. So we also do a kind of geometric entropy where we have a temperature circle and we vary the size of that circle. But we don't keep the parameters of the geometry fixed. We let the geometry back react. So the tip here is always smooth. Okay? And if we're to attempt to do the shrinkable boundary condition story and to remove the tip of this cigar, we have to insist that the boundary condition remembers that we have a smooth tip. And as Zhengbin alluded to, this has a heavy cost, although depends on the point of view, but it has a cost. It means that the boundary condition might be non-local in this time variable. The reason is that to require that there's no conical defect here, we want this integral of the spin connection around this hole to be 2 pi. That by definition is non-local in the time variable. But okay, I'll just accept that as just a fact of life. And the point here is that the gravitational back reaction, the fluctuation of space-time renders the entropy UV finite. That's what's special about gravity. We're not putting in some regulator and then removing it. It's just gravity smooths it out for us. Now, I should say one thing, as a side remark, that we expect this entropy to be clearly captured by edge degrees of freedom, because in gravity, if you were to succeed in quantizing a subsystem, we might also think that the degrees of freedom are always the boundary. And we did realize this story in 2 and 3D gravity. It has this feature that there's no local boundary condition, but I think that's acceptable. At least we gave an explanation in which this makes sense. But today, I want to talk about a more microscopic story, right? So the edge mode story, I view it as sort of some EFT description of some microscopic degrees of freedom. I want to ask about sort of full bulk quantum gravity. The first thing I want to say is that the one-sided bulk subsystem is not a subregion of the original space-time, right? It's just a completely different system. So when I draw this picture now this is a fully gravitating theory, this two-sided black hole. When I imagine via this ER equals to EPR paradigm that this is an entangled sum, each of these one-sided bulk geometries, they end in some way, but that end is not a boundary sitting inside the original space-time, right? For example, this could be a place where some cycle in the internal geometry pinches off. There are these fuzzball geometries that do that. And this A is labeling these kind of microscopic features that allow the geometry to end on one side. At the Hilbert space level, the ER equals to EPR statement is to say that the connected wormhole here is entirely an artifact of the entanglement, which in this case, I'm going to view this as the bulk. So this little disk with the mark here, the mark here is some microscopic stringy degrees of freedom that is complete. What does it mean to have a complete set of such objects? It means in the on the spatial side, it means the entanglement produces a wormhole. But in the space-time, it also has a meaning. So the completeness of this set of space-time ending objects means that there's a shrinkability condition, but which is the same picture I drew earlier, except there's no epsilon here. I replaced the epsilon with some red circle indicating these microscopic degrees of freedom. And this is now a duality. In quantum gravity, shrinkability is just a duality between two target spacetimes, one with a hole, one without the hole. So I refer to whatever is here, I call them entanglement branes. They're stringy objects that induce the topology change. These may also have something to do with cobordism defects that were formulated by McNamara and Vafa. So what is shrinkability in quantum gravity? Intuitively, is a kind of local holography. So what do I mean by that? Local holography is when I take the cigar, which I drew as a disk, and replace the entire interior with just the boundary. Okay? So here I'm claiming there's a more local version of the same thing. I take a little part of the bulk, and I replace it with these stringy condensates. Okay? But I want to remind ourselves that gravity is not 2D, so there's a full 10D spacetime, and what we expect in full quantum gravity theory is that this topology change is actually described by spacetime surgery that does something to the internal geometry as well. So what is spacetime surgery? Is something that takes a p-dimensional disk times a sphere of n minus p dimension. I hollow out the disk and then replace it with a geometry where I fill in the other sphere. So this picture here, I only showed sort of the left-hand side of the direct product, but there's also this other side. And the main thing I wanted to explain was how in topological string theory, this notion of shrinkability really is doing this kind of space-time surgery. That's the reason I brought in topological string. I can make this precise there. Okay, so in case this is maybe not familiar, let me just remind ourselves, what is the space-time surgery in string theory? It is just geometric transition in which d branes dissolve into flux. So how does that work? Let's take our standard example of ADS5 times S5. S5 has some n units of flux going through it. A geometric transition places the flux with d branes. So what we did was we hollow out ADS5, and then we fill in the S5 with R6. So that's exactly the same kind of surgery I described earlier. Maybe it's more familiar to go the opposite way. We start by putting in ND3 branes in the middle of R6. We let it back react in the geometry. And then that produces ADS5. It fills in this other circle here. This S4 was the world volume of the D3 branes. And then the S5 that surrounds the D3 branes, which used to shrink here, right? This S5 shrinks. Now it no longer shrinks. It's supported by n units of flux. Okay, so I want to explain how this works in topological string. So in topological string, there are something called non-compact Lagrangian branes. They play the role of what I call entanglement branes. What do? They factorize the closed strings into entangled open strings, which now end on brane-anti-brane pairs. So this is my cartoon of a stringy factorization. The open strings lit on a different background than the closed strings related by geometric transition. Now, I wanted to explain that entanglement entropy computations in the topological string just uses this type of ER equal to EPR surgery. So this is a word coined by McNamara, by which I just mean the shrinkable kind of boundary condition story where the disk is replaced by the disk with a hole. And the technical machinery that allows these computations to be done is a topological string can be formulated as a large n limit of QD-form 2D Young nodes. That's a theory we have control over, and we can do computations in there. Okay, are there any questions so far? You seem to want to ask it.
Really like this description, because there's more typical ones like we talk with flux and figuring of the manifold transition. So they also follow this category.
Yes, and the conical transition is very important in topological string. That's the famous one. This is a slightly different one that I'll discuss. But can I ask how much time do I have? 10 minutes? Okay, I'll definitely not finish, but that's okay. I'll give an overview of EPR surgery in the A model topological string. Okay, so what is the A model? So we're going to study A model topological string on Calabi-Yau. There are some bundles over a Riemann surface. This OK1, OK2 is like a Hopf bundle, and K1, so it's like a magnetic monopole, with K1 being the Chern class, which is like the magnetic charge. The Calabi-Yau condition is simply that K1 plus K2 is minus the Euler characteristic of this Riemann surface. This is the on-shell condition, right? It's like solving Einstein's equations. The string amplitudes are captured by 2dt QFT living on the Riemann surface. So I'll draw these as a surface decorated by the Chern class numbers. Now the worksheet theory is simple because it localizes to holomorphic instantons that wrap this Riemann surface. And it depends only on the Kähler modulus, which is just the complexified area of the surface. I'll explain what complexified area means. This group of authors independently showed that this TQFT, which I call A model TQFT, just comes from the large n limit of Q deformed 2D Yang-Mills. The Q is e to the IG string. Okay, skip that. So this is the resolved conifold. It's just a sphere with -1 current class. The complexified area is area plus I times the B field flux. So the partition function, this depends on T. It's summed over Young tableaus. There is a dimension factor, which is the quantum dimension of a Q deformed version of symmetric group. There's a bulk factor with the area, and then the L counts the number of boxes in this Young tableau, and Q is e to the IG string. For the expert, the Q deformed symmetric group is the thing that appears here in the Q deformed Cherval duality. Okay, so I want to define a Gibbons-Hawking entropy for the topological string. What does that mean? Instead of having a cigar with this temperature circle, I have a sphere. So let me just vary the size of this angular range around this is the polar angle range, right? But when I vary beta, I have a question. What do I do with the bundle that lives above this sphere? I'm going to fix it at -1, -1. What does this mean? This means I always preserve the Calabi-Yau condition, because when I vary this angle here, I make a conical sphere, but topologically a conical sphere is still a sphere. Euler characteristic 2. So Calabi-Yau condition is preserved, and this is the topological string version of on-shell variation, right? So I compute this combination of derivatives. Now this T you would have thought is beta, but it turns out the topological string partition function doesn't care about the cone, it only cares about the area. So the variation with respect to beta is the same as putting in variation with respect to T. It gives you an answer that looks like, if you know about gauge theory entanglement entropy, it looks like gauge theory entanglement entropy. There's a Shannon entropy term and something that looks like an edge mode term. This 2 log dimension is the standard thing that appears in gauge theory edge mode entanglement entropy. So the question is, what is the state counting interpretation? Okay. Beta is 2 pi, and then we can beta is at polar angle, which is normally 2 pi. But now I allow beta to be any number. I want to test how the partition function responds to changing the angle away from 2 pi. But because this is an area, this thing only cares about area, changing the polar angle from 2 pi to 2 pi n, all it does is change the area. And the partition function only cares about the area. So I replace the beta derivative with the area derivative. Yeah, okay. Okay, so now I need to tell you about the TQFT Hilbert space. So this Hilbert space is the Hilbert space of class functions on U infinity. What is U infinity? Let's start with UN. The configuration space variable on a circle is just the holonomy. I'm thinking now, say, 2D Yang-Mills as a gauge field. A representation basis involves trace in some representation R of this U. But we also have the point here is that we can fix the Young tableau for R as we take n to infinity. That's what it means to talk about U infinity. Better yet, we can think about a winding basis where all the traces are in the fundamental. And now the Kn here can be thought of as the number of cycles in a permutation. So this K is labeling a permutation, and we can fix the permutation at large n. But what's interesting is the winding basis here very explicitly is a closed string basis, meaning we can imagine that each trace U to the n is a loop of string, and there's an oscillator, there's a creation operator that creates a string. So in other words, the closed string, the TQFT Hilbert space on a circle is a string field theory Hilbert space. So that means an element of this closed string Hilbert space is really a wave functional of a closed string. And this closed string actually lives on this non-compact Lagrangian brane. It has topology S1 times R2. And we can imagine that we have embedded a loop of string into this Lagrangian so that it encircles the non-contractible cycle. And that's what this trace U to the n means. It means a loop of string that winds n times. Okay? Now, there's a world volume theory on these D branes. It's Chern-Simons with a particular level related to G string like so. And the key fact is that the string amplitudes in the presence of these branes are closed string states, right? A string amplitude has, for example, here's an example. This geometry is half of the resolved quantum fold. It's actually C3 with a stack of branes. If I study world sheets that sort of wrap this surface but end on a brane at the circle, it's going to be a function of the holonomy on the brane, right? String amplitudes in the presence of D branes depend on the world volume holonomy. But this is just a state in my Hilbert space on the circle because it involves trace R of U. So the idea is that I'm going to factorize this state. I'm going to cut this circle where the closed strings live into open strings, compute its entanglement entropy, and check it is exactly equal to the Gibbons-Hawking entropy that I described before. How is this possible? It seems kind of crazy, right? Cutting closed strings into open strings. The reason it's possible is that cutting and gluing in the TQFT is exactly cutting and gluing string amplitudes in string theory. There's this correspondence. So here's an example. If I give you a sphere in TQFT, I can cut it into two hemispheres, and the gluing integral just integrates over U. But in the string theory, each of these hemispheres have a stack of branes and a stack of anti-branes, and the gluing means I annihilate the brane-anti-brane pairs. So, and okay, for the experts, this is two topological vertices, but maybe no experts here. So we use this cutting procedure to find the entanglement brane that I described earlier. So how do I do that? Well, it's very simple. I take a sphere, and I want to ask, is it a sphere equal to a sphere with two holes, right? So why don't I just cut the sphere? I just remove these small zero area caps from the boundary. If I can do the path integral of this cap, right, then I would find the boundary condition on this circle. And in fact, in topological string theory, in the TQFT, I can compute this cap amplitude. It's given by a state with definite holonomy. This D is a particular diagonal matrix. Q is a phase raised to some power, and I put in a regulator here. And the point here is this, that what this calculation tells us is that the entanglement branes are just the non-compact branes of the A-model topological string. That was the perspective I was after. The thing that I call the entanglement brane are just the microscopic objects in the theory that allow you to split the space-time, but they have to be branes with a special holonomy D. There's something special about this matrix. And at large N, the D branes with this holonomy actually undergo geometric transition. So you have a picture like this where there's two holes, but a sphere with two holes in the string language is really a different background, right? It's a different background because there's a 0, 0 label here. This is actually C3 with two stacks of D branes, but somehow when there are many branes, it gives you back the resolved quantum fold, which is a different background. So this is exactly the geometric transition I was explaining earlier. So now I'm not sure if I have time to explain this, but I want to explain why this D is special. That seems very strange. Why is this special holonomy making everything work? And I want to ask, how do I define a trace? So this is a manifold that doesn't look like a trace, but I claim that it corresponds to this open string system, which looks like a trace, right? Because it looks like the open strings going in a loop looks like it's doing a trace. The only caveat is this D here. I chose a special holonomy. Okay, so in this slide, I've modified the expression for D by including an e to the ig string times n here. This n wasn't there before. It turns out that it's okay. This D also works. It also implements the same geometric transition, but it does so in a complicated way. There's a double limit. You take n to infinity with ig string n fixed. This looks like a twist coupling. And then you take this t prime here to infinity. It produces the same geometric transition, but this complication has a nice physical interpretation. First interpretation is, with this new D, this matrix here, it is actually something called the Drenfeld element of a quantum group. Its job is to produce for you the quantum dimension of a representation of UN. You take the ordinary trace of this object, it gives you the dimension. Okay, I might have to skip. Let me skip this story here. I think I'm going to run out of time. So the point here is that there's something called a quantum trace, which is just to take an ordinary trace and I insert the D, right? I'm just going to put the D into the trace and then call that the quantum trace. That is a trace that maybe not so familiar in high energy, but it's very common in condensed matter for people who study anion systems. So we're seeing anion physics emerge. Why? I claim that the open string endpoint becomes an anion. There's something anionic about the topological string. Okay, so why is that? So it turns out that the whole job of this D, the way I have written it, it is exactly the holonomy that turns the non-compact branes into compact S3s. That is the only job of that special holonomy. And the S3 is a compact brane, which means it's dynamical. So we have now dynamical transformance theory on these two S3s. Now there's an open string instanton stretch between these two S3s. What does it do? It inserts two Wilson loops that are correlated. The representation of this Wilson loop is the same as the representation of that Wilson loop. In transformance theory, a Wilson loop insertion is computed by ribbon graphs that attaches itself to the Wilson loop. That's what these ribbon graphs are. This, in the string theory, is an interaction between the brane and the string endpoint. And this interaction turns the open string endpoint into an anion. And an anion satisfies a different type of trace, right? If you study the trace on anion Hilbert space, it's not the normal trace, it's the quantum trace. So the anion I'm talking about are just the Chan pattern factors of the open string, but because they become anions, I now have to give you a new trace, and this new trace is exactly what produces the geometric transition. A little more detail, what is are we tracing over? So Zhenping was asking about what is the V, what is the subregion? It's the open string Hilbert space, which is now, rather than being class functions on U infinity, is any function, any square interval function on U infinity, but with this Q deformation here. So I want to explain that. So let's take n finite and Q equals 1. Then it's very sort of intuitive that the L2 of UN is spanned by such a basis. It's just a product of the matrix elements of a unitary matrix, Uij. These are really Chan pattern indices, so this is describing an open string stretch between two branes. What's different about Q not being 1? When Q is not 1, we should think that these matrices do not commute. They satisfy a braiding according to an R matrix. And then what does it mean to take n to infinity? Well, we use the same trick as before. We use something called Cherval duality. We replace, we symmetrize and anti-symmetrize these indices according to a Young tableau, and we fix the Young tableau as we take large n. In this story, the Hilbert space now take this form. This is called the Peter-Wald theorem, but all we have to know is that this statement is to say that matrix elements in all the irreducible representations of U infinity will span the Hilbert space. These are the wave functions of my open string. Okay, so let me end on this slide. The point is that now we really have a trace interpretation. Now these non-compact branes, there are open strings attached to them, and they have a Hilbert space on which I define a trace, right? And this trace I can write out very explicitly. I replace the Q here with the insertion of the D. And it turns out that if I do this trace properly, I get back the resolved counterfold. So this quantum renormalized trace is doing the geometric transition for us. Now I added this formula just for Marcos, who's not here. But if he's watching, how did this work? So I did something miraculous. I traced over UN indices, right? So I should get UN dimensions. But the answer here is symmetric group dimensions. How is that possible? I count UN representations, but then I get symmetric group dimensions. That seems like a magic, right? Well, this magic came from Marcos, Vafa, Mina, Kamrum, and Albrecht. There's this formula that when I take a large n, large T prime limit, that's why I did this complicated limit, it produces for me a symmetric group dimension. And that's why I used in this, going from this line to that line. And that's how the hole is closed up. That's how the geometric transition works. This is not a coincidence because this magic formula was exactly involved in this Gopakuma-Bava duality in topological string, which is the geometric transition for topological strings. So I feel like I'm probably out of time, or do I still have any time? 1 minute. Okay, so I'll end on this slide. We can factorize the Hilbert space. It's very simple. I take the holonomy around the circle was a proxy for a closed string. I write the holonomy as the product of two Wilson lines, one on each interval, that's the open string. I now stick it into the quantum trace. The quantum trace, I can write out the trace explicitly. It has this extra factor of the d because I have to insert something to make this a quantum trace. And the right-hand side is the tensor product because this RAB is an open string wave function. This RBC is another open string wave function. And now I can define a QT-form entanglement entropy where I use this funky trace on the open string Hilbert space, and I reproduce the Gibbons Hawking entropy. And now to go back to Zhengbin's sort of question, so in both the topological string and as I mentioned in gravity, there is something non-local about the shrinkable boundary condition because the holonomy in time was not 1. You see, anytime the holonomy around the time direction is not 1, that's a non-local condition, okay? But that non-locality has been packaged into a well-defined trace. What does it mean for the trace to be well-defined? It has a nice operational meaning that people in condensed matter know. But it's entanglement entropy. It should be measuring something operational. In this case, it measures the number of anionic Bell pairs that you can distill from this entangled state. If I delete the word anionic, this will be the plain usual definition of entanglement entropy. So this indicates that perhaps this is not a completely microscopic story. There might be the fact that the trace has been modified. It sounds like the type 2 kind of thing. And remember, I also regulated this trace. I inserted some epsilons there. However, the way it goes beyond the normal discussion is that I really found some microscopic objects. This theory has brains, and I cannot talk about the closed string entanglement entropy without referring to those brains. Even in the purely closed string theory with no open strings, if I ask how do I compute the entanglement entropy, I have to cut the closed strings with some objects, and those are the brains. Okay, so I think this is, I'll just end with some comments here you can read, and yeah, I think I'll end here.
Okay. Thanks, Peter, for the very interesting talk.